Hello again. This is video lecture 33.2, and we're going to discuss in chapter 33 sections 5, 6, and 7. And we are transitioning here really fully to a discussion of what is called optics, the behavior of light. But remember, we know now that light is a phenomenon known as an electromagnetic wave. And everything that we're going to talk about in this video lecture can be demonstrated mathematically with the four Maxwell equations, also demonstrated empirically by experiments. And we're going to summarize these key results. And a lot of the phenomena we're talking about here are rather interesting and can be demonstrated pretty easily in a lecture hall or in a lab. Okay, in section 5, we're going to talk about the phenomena known as reflection and refraction. So here's what we're thinking about. We've got two materials. Consider them both to be what you would call in everyday life transparent materials. And what that means for most people when you say that is that you can see through them. In other words, light, the electromagnetic wave with wavelengths in the visible region of the electromagnetic spectrum, that's what light is, can propagate, travel through a transparent material, whereas in other materials that aren't transparent, it's either fully reflected or absorbed. Okay, so we have two transparent materials. Let's just consider them to both to be kind of block-shaped, or in a container that's block-shaped. And there will be what's called an interface, where the two materials meet. And we will shine light, we will send in an incident electromagnetic wave from one material towards the interface with the other. And we can swap the roles as to which way the light comes towards the interface, from the top material, if you like, or from the bottom material. You could do experiments with both. But however you do it, you send in light towards this interface between one transparent material and another. What will the light do when it gets to the interface? That's the question for this section. And the answer is, in general, for two transparent materials put together with an interface, is two distinct things can happen together. And they are called reflection and refraction. And they will occur at this interface. Now, in order to study the refraction part specifically, we need to introduce one new idea. It's the concept of the index of refraction of a medium. A medium just is another word for a transparent material. So what is this thing called index of refraction? Well, we have to talk just a little bit more about these electromagnetic waves that we're calling light. We've studied them so far under the assumption that they were traveling in what's called vacuum, complete emptiness, absolute emptiness, the lack of any atoms of any kind whatsoever. That's what vacuum means. And it's well known that electromagnetic waves, when traveling in vacuum, travel at speed of 3 × 10⁸ meters per second, denoted by the symbol little c, and often just called speed of light in vacuum. But when light travels through a transparent material, even air, which is quite diffuse, as you know, but let's imagine clean water as a transparent material. That's more complicated. The electromagnetic wave has to do some pretty complicated interactions with all the atoms and molecules inside the material, because the atoms and molecules, at least the ones closest to the surface, will absorb the electromagnetic wave and then re-emit it as if they were little transmitting antennas. And then the neighboring atoms or molecules will absorb those emitted electromagnetic waves and then emit new ones. And it will continue kind of like a chain reaction, one row, if you like, of atoms or molecules after another. And that's how the light propagates through an actual transparent material. But that process takes takes some time, a finite amount of time. By the human standard, it's amazingly fast, but it does take a finite amount of time. So the net effect is that when light travels through a transparent material, like water, its speed at which it travels is less than c, less than the speed of light in vacuum, less than 3 times 10 to the 8 meters per second. And this can be measured. So the index of refraction is a way to measure how much a given material slows down the light waves. The symbol for index of refraction is just a lowercase n, and it is defined to be the speed of light in vacuum divided by the speed of light in the medium. So each medium has its own index of refraction. We use the symbol c for speed of light in vacuum. Please only use little c for speed of light in vacuum. And we use the plain old common symbol for speed, v, to denote the speed of light in any kind of medium, anything that isn't vacuum. Please follow those symbols or you'll be hopelessly confused. So we take the speed of light in vacuum divided by the speed of light in the medium. C divided by V. But V is less than C for any medium. So for any medium, N, the index of refraction, is bigger than 1. Now, by definition, for a vacuum, N is exactly 1 because it's C over C. But for any ordinary medium, N is greater than 1. Now, it may not be much greater than 1. For example, in air, the index of refraction, 1.00029. That's so close to 1 that we will approximate it to be 1. But for water, you might find that the index of refraction is 1.33. Okay? So you can think about how much that means the speed of light is slowed down in water compared to its speed in vacuum. Notice, by the way, that this new quantity we've defined, index of refraction, is unitless, dimensionless. It has no units because it's a ratio of 2 speeds. Now, the speeds themselves have units, and you can, right? And you have to know what those are when you plug in the numbers for C and V because they have to be the same units for C and V. But N has no units. Okay, so what you want to remember again is the larger the index of refraction, N, the more the light is slowed down in that material, that medium. Okay, so now let's imagine doing some experiments where we send in a light beam at an interface between 2 different media or materials. And that's what the photograph on the left is showing. It's showing a tank of water surrounded by air. So here's the interface right here between the water and the air. And we're going to send in light with this projector type object. So we'll draw what's called a ray. That's the incident ray. It shows the direction the incident light is coming in. We take what's called the normal to the interface as a perpendicular line. That's very handy. And then we look to see what happens to the light. And the photograph shows, if you look carefully, exactly what happens. Some of the light is reflected back into the air that way. See the beam? And some of it is refracted into the transparent material down here, water. Okay? So we get both reflection, that's where the part of the light that bounces off the surface and comes back up into the incident material, and part of it is refracted, bent. Refraction just means bent, and goes into the material. So there's a photograph showing you in the real world what happens. Now on the right, we have a schematic representation, which enables us to add more information. Let me expand it so you can see it a little better. So we have an interface between air and water. There's the normal to the interface with the dashed line. See, it's just perpendicular to the interface. Here's the incident ray coming in. right along here, showing the direction the wave is traveling towards the interface. These little tick marks perpendicular to the incident ray represent wave fronts. You can think of those as planes, or representations of planes. And in those planes, the electric and magnetic field vectors are doing their oscillating. So these planes, these wave fronts, are going this way and in and out of the screen. And we keep track of what's called the angle of incidence. Angle of incidence, theta 1, which is measured relative to the normal. Be careful. And it's just the angle between the incident ray and the normal. Okay, some of the light will be reflected. And so there's the reflected ray. And you can measure the angle between that ray and the normal. It's labeled there, theta 1 prime. That's called the angle of reflection. Look carefully, it's labeled theta 1 prime. And part of the light is refracted or bent into the transparent material and travels that way. And so now we want to measure the angle that that refracted ray makes with the normal. It's measured down here, but it's still relative to that dashed line, the normal. And that's called the angle of refraction. And this picture labels that theta 2, right there. Okay, so that's what happens. The incident ray comes in at an angle of incidence theta 1. Some of it's reflected back up at an angle of reflection theta 1 prime, and some of it is bent, refracted into the new material at an angle of refraction theta 2. How are these various angles related to each other? Well, the answer is right here on the screen in front of us. Experiments and the 4 Maxwell equations show, this one's an easy one, the angle of incidence theta 1 is equal to the angle of reflection theta 1 prime. Now this is assuming the interface is nice and smooth and flat. Theta 1 equals theta 1 prime. Angle of incidence equals angle of reflection. But the angles theta 1 and theta 2, for the picture there with air and water, not equal. In fact, the picture clearly shows if we have air and water together like this, that the theta 1 angle, the angle of incidence, is larger than the theta 2 angle, the angle of refraction. You see that in the picture? What is the relationship between theta 1 and theta 2? The angle of incidence and the angle of refraction. Again, from experiment and from the Maxwell equations, you can show that the following equation is true. Now this is where we need the index of refraction. There's an index of refraction for the incident medium, which happens to be air in this case, and an index of refraction for the refracting medium, which happens to be water in this case. Your authors and the picture will use the symbol generally of N1 for the index of refraction of the incident medium, and N2 for the index of refraction of the refracting medium. And with those symbols in mind, here's what that law of refraction says. N1 times sine theta 1 must equal N2 times sine theta 2. It's the product of the index of refraction and the sine of the angle in the two materials that must be equal. Historically, this result is also called Snell's law, but you could just call it the law of refraction. Although calling it a law is a bit too overstated. It's not that important. It's handy, though. Note then, if this equation is to be satisfied, so far experiments show that it must, there's some general conclusions we can draw about refraction at an interface. Okay? What if you have, which is the picture we're showing you, the situation where N1 is less than N2. So if the if the medium of incidence is air and the medium of refraction is water, then N1 would be the index of refraction of air, and N2 would be the index of refraction of water, and the index of refraction of air is less than the index of refraction of water. Okay? What does the law of refraction tell us when N1 is less than N2? Well, it all boils down to this equality right here. The product of N and sine theta for each material must be equal. So, if I have a situation where N1 is less than N2, then it must be the case that theta 1 is greater than theta 2, right? Because it's got to make up for the smaller n on the left. You've got to think about that equation a little bit. But if N1 is less than N2, then the law of refraction requires that theta 1 is greater than theta 2. And the refracted ray angle is the smaller one, and that's what the picture up here shows. Yes, the picture shows theta 1 is larger than theta 2. So here's what we say. The refracted ray in that case is bent toward the normal. Because if I go back up to this picture, and I extend the incident ray in a straight line, just for a visual reference, into the refracting medium like that, that would be the direction the incident ray would travel if there were no refraction at all. But see what the refracted ray did? It bent away from that black line that I just drew towards the normal. It got closer so that theta 2 could be smaller than theta 1. And so in a situation like that, we say the refracted ray is bent, or refracted, toward the normal if N1 is less than N2. Now let's turn that around, because you could have a situation where N2 is less than N1. That could happen easily enough if the incident medium, remember N1's for the incident medium, is say water, and the refracting medium is say air. So let me draw a new picture. Let me draw the tank of water surrounded by air up above. So there's the interface right along. And let me draw a normal to the interface for reference. But now let me have a light coming in from the water side. That's now the incident ray. Pretty easy to tell by the arrow on it. So this angle right here would be theta 1, the angle of incidence. And this material, water, would be denoted, its index of refraction would be denoted N1. N1 for the index of refraction of the incident medium. And so the index of refraction N2 would be used for air. So now we have a case where N2 is less than N1. What does the law of refraction require? It requires theta 2 to be greater than theta 1. So the angle of refraction is larger than the angle of incidence. So if I draw this extended line into the second medium for the incident ray as a visual reference, then the refracted ray has to be bent away from the normal and beyond that line. So something like that. And then theta 2 would be all of that. Remember, the angle's measured from the normal. And it's clear that theta 2 is larger than theta 1. And we say the refracted ray is bent or refracted away from the normal. That's a very handy little rule of thumb to help you remember when light is incident on an interface, which way will it be refracted as it goes into the new material, towards the normal or away from the normal? Okay, so those are some of the basic concepts related to reflection and refraction. Now let me add a little more real-world complication to it. One of the things that happens in a medium, many different materials, is that you get a phenomenon that we call chromatic dispersion. Well, sounds fancy. But here's what it means. Chromatic means colors. In visible light, the color that one sees is determined by what's called the wavelength of the light. Longer wavelengths in the visible region are more red. Shorter wavelengths are more blue and violet. So when we say chromatic, when we're talking about light, we're talking about color, and what we're really talking about is wavelength. So chromatic dispersion is merely the phenomenon where, for a given material, the index of refraction, n, can be different for light waves of different wavelengths. Lambda is the symbol, remember, for the wavelength of a wave. And here the units are nanometers because we're talking about visible light. And we're down at the short wavelength end, we're talking about more violet colored light. And at the long wavelength end, we're talking about more red light. And what this graph shows, it's for a particular kind of transparent material called fused quartz, that as the wavelength of the electromagnetic wave, the light, gets larger, the index of refraction gets smaller. Now, you might not say it's a huge effect. Notice the range on the y-axis is ranged from 1.48 to 1.45. But it is large enough to be definitely noticeable in its consequences. But that's a helpful thing to remember. And that's generally true for a lot of dispersive materials. As the wavelength gets bigger, the index of refraction gets smaller. What's one of the consequences of that? Let's talk about it. Let's go back to our kind of standard picture of an interface between two materials. Let's take air and glass. There's the normal. See the dashed line perpendicular? Here comes the incident light, and this is called, notice, white light. Now, what does that mean in optics? Well, white light is what you generally see coming out of light fixtures, light bulbs, and the like. And it generally means a mixture, more or less equally, of all the wavelengths of visible light. From the low wavelength end, 400-ish nanometers, to the long wavelength end, 800-ish nanometers. You mix all those together, you get what's called white light. So if the picture says, well, you've got incident white light, it means you've got electromagnetic waves coming in with a range of wavelengths. Incident on the interface at an angle of incidence theta 1. Some of that white light will be reflected at angle of reflection theta 1. What about the light that's refracted? All right, here's a dashed line extending the incident ray, just for visual reference. And we need, I'll write it over here to the side, the law of refraction to help us. And we're looking at material 2, happens to be glass, the refracting material. Well, basically, the larger the N2, the smaller the theta 2. Sorry, that's not visible, is it? The larger the N2, the smaller the theta 2. Because you still have to be equal to the N1 sine theta 1 on the other side. Okay? So just remember, the larger that is, the smaller that is. Now, let's consider the extremes in the white light, the extreme wavelengths. Blue on the short wavelength end and red on the long wavelength end. And our graph of the index of refraction versus wavelength shows that the N for red light is less than the N for blue light, blue/violet. So if the N for red light is less than the N for blue light, then the theta for red light must be larger than the theta for blue light. And so this is exactly what the picture shows, right? The theta 2 refracted for the red light is larger than the theta 2 refracted for the blue, by what may seem like a small amount, but what is definitely observable. And this kind of dispersion like this, right, what it's doing is it's taking incident white light, where all the wavelengths were traveling together, and it's spatially spreading them out. This dispersion and refraction. And this is exactly what a prism does, yes? Some kind of transparent material, like some kind of glass, and white light comes in, but then different wavelengths are refracted by different angles because of the different index of refraction, and so it separates the white light into the individual wavelengths, and you get the pretty rainbow effect. It's chromatic dispersion that's going on. That's a handy thing to remember. That's part of what gives you rainbows. Okay. Next, section 6. Another fascinating phenomenon, and technologically quite important these days. Section 6 talks about a phenomenon called total internal reflection. So, here's what we're going to talk about now. First, let me zoom in and get this so you can see it. In this schematic drawing on the left, we have our standard picture with an interface, a flat interface between two materials, air and glass. And we have a source of light, a little pinpoint source of light, S, in the glass that's sending out light rays from the glass towards that interface. So notice then glass is the index, is the material of incidence. This is the incident material. And it's air that's the refracting material in this case. Okay? And it shows, labeled little a through little g, a number of different rays coming out of that pinpoint source S. Maybe it's coming from some kind of a laser that we've piped the light in. Don't worry about how we do it. Okay, but the key thing is that the light is incident on the interface, with the incident side having a larger index of refraction than the refracting side, right? The N of glass is larger than the N of air. I'll write it out explicitly. The index of refraction of glass is larger than the index of refraction of air. Now let's just look at some of these rays. Ray little a is kind of extreme. The ray goes straight towards the interface along the normal. That means theta 1 is 0. You get some of it that's reflected back. See the arrow coming back? And some that is quote-unquote refracted going outward, but the law of refraction says that if theta 1 is 0, then theta 2 is 0. So the refracted ray just goes straight out. Okay, ray B comes in at a little bit of an angle. The theta 1's pretty small. Some of it's reflected, and some of it is refracted. There's the normal. Into the air at an angle theta 2 that's larger than theta 1. Now look at ray C. That's coming at the interface at a slightly larger angle of incidence than B. Slightly larger theta 1 than in B. Some of it's reflected back into the glass, and some is refracted outward at a theta 2 larger than theta 1. Now look at ray D. Approaches the interface at a slightly larger theta 1 than in case C. Some is reflected, and there's the normal. Some is refracted at a theta 2 larger than theta 1. See, there's an interesting limiting case approaching. We might as well draw it now. It's ray E. The ray comes in at an angle, theta 1, to the interface. And that angle, theta 1, well, some of it gets reflected back, of course, but the part that's refracted has to come out at a theta 2 larger than theta 1. And in this limiting critical case, the refracted ray comes out right along the interface. That means the theta 2, because that's a right angle right there, is 90. You can't get a theta 2 larger than 90. It's impossible. So this picture, little e, is a critical case. In fact, the angle of incidence, the theta 1 here, is so important, they call it theta critical. That's a theta c. And it is the angle of incidence on the glass side such that the angle of refraction is 90 degrees. So here comes an interesting question. Look at ray F. What if I take a ray that is incident on the interface at an angle theta 1 here, larger than theta critical? No light gets refracted. Nothing. Nothing out there. It's all reflected back. And in ray G, that's even more extreme. The angle comes in, the light comes in at an angle of incidence theta 1 to the normal that's larger than theta critical. None gets refracted out into the air. It all gets reflected back into the glass. And so if we are having a situation like this, where all of the rays are reflected back, that's called total, pardon my writing there, internal reflection. And that's the physics behind fiber optic cables. You send light down what's called a light pipe, which is just some transparent material with an index of refraction larger than that of air. And you make sure that as the light travels down the light pipe, that when it hits the sidewalls, it always hits them at an angle theta 1 larger than this critical angle. Then it's always going to be reflected fully back in to the cable. And over here on the right, we have a photograph showing the actual phenomenon happening. Right? It's a tank of water. Here's the interface between water and air above. You can see the source of the light is just right down there in the water. And some of the light goes straight up to the interface and then comes straight out, and part of it's reflected. Here's light that comes in at an angle less than the critical angle, so some gets refracted. This light comes in also less than the critical angle, so some gets refracted. But this light comes in at an angle greater than the critical angle, and it all gets reflected. So the critical angle is something between that angle and that angle. And it's important to be able to calculate what that critical angle is, so that if you wish to have your light to be totally internally reflected, then you need to make sure that it's always incident on the boundary at an angle greater than the critical angle. So let's calculate that. Let's calculate the critical angle for total internal reflection using the law of refraction. Now here I like to get rid of the 1 and the 2 subscripts that the book uses, because it's easy to forget what's 1 and what's 2. So my subscripts are going to be INC, referring to the incident material, and REF, referring to the refracted material. Then the law of refraction says N incident sine theta incident must equal N refracting sine theta refracting. And let's have the light coming in at an incident angle at what's called the critical angle. What that means is the refracting angle is exactly 90 degrees. So, just to be clear, I'm now looking at, let me declutter my drawing up here. I am now looking specifically at this ray going like that. Okay? That's what I'm looking at specifically. All right, so the law of refraction then says N incident sine theta critical is equal to N refracting sine 90. Oh, but the sine of 90 is 1. So just solve for sine theta critical. It's N refracting over N incident. Where remember, N refracting is less than N incident. That's the only way you can get total internal reflection to occur. N refracting must be less than N incident. And then with knowing the N's of the refracting and the incident materials, you can calculate theta critical. And there is a schematic of a fiber optic cable showing light coming in at one end, and then every time it hits a boundary, it hits the boundary at an angle greater than theta critical and is always then reflected back in. Okay, one more interesting optical effect in this lecture, video lecture. Section 7, a way to polarize an electromagnetic wave, light, by means of reflection. We learned already in the section on polarization that the common way you get polarized light is you send unpolarized light through a polarizing sheet, which is made of long chain molecules that are all lined up in a particular direction. And then the light that gets through is linearly polarized along the direction of what's called the transmission axis of the sheet. And that's a way to get polarized light. But that's not the only way it turns out. You can also get polarized light if you have reflection from a flat interface, if that reflection happens just right. So we're going to talk about polarization by reflection and calculating what's called Brewster's angle. So here's what's happening. We've got an interface between two materials. Again, we'll say air and glass. We'll take the index of refraction of air to be basically 1, and the index of refraction of glass is whatever it is. This says n equals 1.5. It doesn't really matter what that number is. Okay, we've got incident light coming into the interface on the air side. There's the incident ray coming in at some angle of incidence. And this light happens to be unpolarized light, as would be, say, sunlight from the sun. And the way they represent that, it's kind of hard to see, is they show that the electric field is oscillating both up and down in the wavefront, perpendicular to the ray, and the electric field is oscillating in and out, just represented by a dot. The electric field is oscillating in both the up and down, as it were, perpendicular to the ray direction, and in and out, perpendicular to the ray direction, unpolarized light. And what experiments show is that if the unpolarized light comes in at an angle of incidence that's just right, it's labeled there theta b, then when you have your reflection and your refraction, the reflected ray will come out linearly polarized, with the electric field oscillating along the in-out direction, perpendicular to the ray. Notice that that direction is then parallel to the interface. That's what ends up being the direction of the polarization. And then, of course, you have a refracted ray, which is still unpolarized at an angle of refraction, theta r. And the angle of reflection is the same as the angle of incidence, both labeled theta b. And it turns out that if the angle between the reflected ray and the refracted ray is 90 degrees, that's the important thing. The angle between the reflected ray and the refracted ray is 90 degrees. That's when you get this polarization of the reflected ray. So it's not hard using the law of refraction to calculate what that magic incident angle theta b is. Okay? You just have to apply the law of refraction plus this constraint. Theta b plus theta r must be 90. See how I know that? There's theta b, there's theta r, that's 90. So theta b plus theta r must equal 90 because those three must add up to 180. All right, now let's apply the law of refraction. I'll write it this way. Incident, sine theta incident, well, that's b, theta b, must equal n refracting sine theta refracting. The picture calls that theta r. But that's n refracting sine of theta r, which is 90 degrees minus theta b, yes, because of that constraint. So, n incident sine theta b must equal n refracting, well, it turns out sine of 90 degrees minus theta b is equal to the cosine of theta b. Now it's easy to solve for theta b. Divide by cosine, and you get tan theta b equals n refracting over n incident. And then take the inverse tangent of both sides, and you have a way to calculate what's called the Brewster angle for reflection from an interface between two materials. And if the incident light is unpolarized and comes in at that Brewster angle, the reflected light will be linearly polarized with the direction of the electric field oscillation parallel to the interface. This tends to happen when light from, say, the sun is shining on the surface of a calm lake, for example, on a sunny day. And a person is standing over here looking at the pretty vista, the pretty view. The light that's coming into their eye may be pretty bright from the reflected ray, but it is linearly polarized with the electric field parallel to the surface of the water. So if the person puts on a pair of sunglasses in front of their eyes with the transmission axis perpendicular to the surface, then all of those horizontal reflected, all that reflected ray gets absorbed by the polarizing sheet in the sunglasses. And of course, you can have direct sunlight coming in to your eyes from the sun, so that gets through. At least part of it does. But none of that reflected ray gets through your sunglasses. And so it reduces the glare that you would see on such a sunny day. And that's commonly the way the sunglasses are used. Okay, so we'll finish with the class engagement exercise for Blackboard. And it goes like this. We have three figures, little a, little b, little c. They all show a ray that's incident on an interface between two different materials. And the pictures show the index of refraction for each of the materials. So for example, in case A, the incident ray is coming to the interface like so, with the incident index of refraction 1.4. Then we get some refraction into this material with an index of refraction 1.6. Be careful, the shaded side may not have the larger n, not necessarily. And it's not showing, by the way, the reflected ray in any of these pictures, even though that in principle would be there. In case B, you can see the incident ray coming up on the interface, where the n is 1.6, and then there's the refracted ray into the material with an n of 1.8. And in picture C, here's the incident ray with index of refraction 1.5. Here's the refracted ray into the material with n of 1.6. The question is quite simple. Which of the three drawings here, if any, show physically possible refraction? Which is physically possible to happen? That's what you have to answer, okay? And we'll talk about reflection and refraction in our class. And that's all for this video.